Hey guys, let's get started right away. I'm going to give you about 3 minutes to complete that graph on the right. And we'll double check it. We'll do a little bit of work beyond the video, the intro video, and then we're going to spend the last half of our class reviewing your quizzes from last time. What I think very definitive system as to how to do this. Do you guys remember what you're supposed to find first? Zeros. Yeah, you're supposed to find out where f prime would be 0. So f prime would be 0 wherever that graph of f right there has a horizontal tangent line. And how many places do you see a horizontal tangent line on that graph? 2 places, yeah. So I would say right there and right there. Don't write that on your graph. I'm just circling those. That is where f has a horizontal tangent line. So that would be where the slope of f is 0. So it would be where f prime is 0. So as I get started graphing the graph of f prime, I'll do it in red. I would put a 0 here and another one right about there at 3. So those would be my 2 zeros. I'm going to be graphing f prime in red. So always start with those regardless of anything else, really. I would start with that. You guys have any questions on that part? Okay, so from here on out, it's basically where is f prime positive or where is f prime negative. And so I'll just try to lead you through hopefully some logical thoughts here. So this green stretch right here, would you say that f, the graph of f, is increasing or decreasing? Increasing, right? So if f is increasing, the slope of f would have to be positive. And if the slope of f is positive, that means f prime is positive. Yep. And if we're going to try to graph f prime and f prime is positive, where do positive values show up on the graph? Above. Yeah, above the x-axis. And so it would have to be up here somewhere. But don't I know that I'm heading towards 0 when x is negative 3? Mm-hmm. So I would say it's got to look something along the lines, it's got to look something along the lines of this right here. Now, if you had this, I'm okay with that. If you had this, I'm okay with that. If you had this, why am I not okay with that? Yeah, that's f prime being negative, and that's not true. So I'll just leave it with my first one right there. I think that would be fine. Any questions on that part? Okay, so again, as far as trying to structure your thinking, I'm going to look at this blue stretch next. So from here to right about there, what could we say about f? F is increasing or decreasing? F is decreasing, and if f is decreasing, the slope of f is negative, and if the slope of f is negative, f prime is negative. Starting to see it? Hopefully it's making sense to you. So if f prime is negative, that means, there we go, that the graph of f prime needs to show up on what part of the graph? Underneath, yeah, underneath the x-axis. But I know that I've got to loop back up towards 3, and so I would do something like that. If you had that, that's great. If you had this, that would be just as good. If you had that, that's fine. That's fine. That's fine. All these are good graphs. If you have this, that's a problem. Make sense? Okay. So I'm trying to give you a hint about how I would grade something like this. Make sense? All right, and then the last stretch over there, I'll be highlighting that in purple. Looks like this. So on that stretch, we could say that the graph of f is increasing or decreasing. And if the graph of f is increasing, that means the slope of f is positive, and that means that f prime is, and it'll show up where? Above the x-axis. You got it. So I would just complete this by doing something along those lines, and I'd be done. I went a little bit too far there, I guess. Can only have to stop right in there. All right. Do you guys have any follow-up questions? Yeah, go ahead, Sam.
So it looks like each time, like this was a cubic.
Maybe.
And then it went to a parabola.
Maybe. We don't know. So, and you're thinking a cubic, the derivative of a cubic is a parabola. Mm-hmm. That is true.
And like a quartic or whatever is fourth, that one looks like a cubic.
Yeah, but we don't know that this is even a cubic. This could be a piecewise of 2 crazy rational functions. We just don't know. So be careful. Like the statement you said at the start is definitely true. The derivative of a cubic is a quadratic, and the derivative of a quadratic is linear, right? Those things are totally true, but I would suggest that instead of thinking of it like that, be more flexible and just use the little system that I've given you. But if you see, it looks like, yeah, that's cubic-ish, therefore the derivative of that should be quadratic-ish. I'm okay with that, but I would encourage you to think of, all right, what's going on with the zeros? Where is f prime positive or negative? That system is very adaptable and very broad in general. The whole polynomial thing is not. It could lead you astray. So consider. But what you said was true. Other questions? Anything at all? We're going to do one more practice like this here in a minute. Thought I'd give you a chance to ask if you wanted to before we move on. We're good? Okay, cool. So then the video covered differentiability. I hope that you've started to get the sense that the videos are not like, oh, if you feel like it, it's cool. Videos are like an integral, no pun intended, part of the class. I got a couple courtesy Snickers. That's good. Yes, so if you're not watching the videos because it's like, I don't want to, or I forgot, you definitely should be doing that. They're supposed to be intro videos, and so if you watch them after the fact, that's kind of the reverse. But it would be better for you to watch them afterwards than to not watch them at all. Okay, so if you see those assignments coming up on your little Schoology coming up stuff, those are real assignments intended to really do something, as opposed to something just like busy work, waste your time, that kind of thing. They're very, very important. So anyways, we are going to talk about differentiability right here, and I'm going to go with about that. I think that'll work. Okay, so differentiability, if you watch the video, you heard me say something about differentiability is not speaking to like your talent and your ability to figure out derivatives. It's talking about some graphs are going to have places where the derivative simply doesn't exist and places where the derivative does exist, right? And there's going to be several characteristics that bring those things about. And watch the video, you'll see stuff about sharp points and discontinuities and vertical tangent lines and all that stuff. It's in there. And you'll want to know about that for sure. So if you haven't watched the video, this is another reminder to do so. We're going to work with that idea right here. And looking at that graph of f, as we look at this question right here, it says find the x value where f is not differentiable. Just looking at the graph, what do your eyes tell you is that place of non-differentiability when x is 0? And what do you see going on at x equals 0? The sharp point. Yeah, you can see it looks pretty sharp. I will rarely, if ever, call on your powers of observation to notice that, because like your definition of sharp point and my definition of sharp point could be a little bit different. So I'll usually call it out and be like, hey, that's a point of non-differentiability, or there's a sharp point right there. So I'm not going to like mess with you like visually and be like, man, I'm sorry, your eyes just are not as strong as somebody else's, and so you didn't see it. I'm going to try to make it really obvious, or I might just call it what it is. That makes sense? And this one is like relatively obvious, right? Sharp point. Okay, so we found that, so we could say x equals 0 is where this point of non-differentiability happens. But then it goes on to say, not only do we have to identify it, we are supposed to use the definition of the derivative with one-sided limits to essentially rigorously prove what you just said, that x equals 0 is this. And so if it says use the definition of the derivative with one-sided limits, and you write this, there is a sharp point there. That is just simply not following directions, right? That's not using one-sided limits, not using the definition of the derivative. It's a good description, but it's not the rigorous activity that this is asking you to do. So good description, but not a good justification. Here's how you do it. I want one-sided limits, and so it looks something like this. The limit as x, you know what, sorry, let me give myself a little bit more room here. I'm going to say the limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0. I hope you recognize that as the definition of the derivative, right? From the left, at least. So let's look at the graph. So if you look at that graph up above there, the graph of f, as you approach 0 from the left, what would you guys say is the behavior of f prime? First of all, as you approach from the left, is f prime positive or negative? Clearly positive. How could you guys describe that left piece on the graph? Because it is it's linear, yeah. So it's looks like it's linear to me. And if it's linear, we should be able to find the slope. And I agree, it looks like it's a slope of 2/3. So I'm going to just write, as I approach 0 from the left, it appears that f prime is 2/3. Sometimes it'll be relatively easy to notice that because it's linear. But as you approach 0 from the right, it's not quite so easy, is it? So if you write limit as x approaches 0 from the right of the exact same difference quotient, we can't really say, hey, it's 2/3 or some number like we said with the left piece. What could we say based on the information given? All you really have is a graph. The opposite direction, Max, you said?
It's negative.
Negative, same idea, right? It's going the other way. Negative is a good descriptor. We can't really get more specific than that, can we? We can't say that it's -1 or -2 or something like that. But we can say for sure, based on the graph, that as you approach 0 from the right, the derivative of f very clearly appears to be negative. And as I try to connect these two statements here, wouldn't it be fair to say that there is no way that something that is 2/3 could equal something that's negative, right? And so the way that I connect them would just be to say they are not equal. So the limit as we approach 0 from the left, being 2/3, does not equal the limit as we approach 0 from the right, which is negative. Sir? This is as specific as we can get, right? I can say 2/3 pretty confidently. I can say negative, but I can't go more specific than negative. So here's my conclusion. Because the derivative from the left and the derivative from the right are not equal, we could say, therefore, f is not differentiable at x equals 0. It's supposed to be a 0. There we go. Is that, Jake, does that kind of close up what you were thinking about?
Well, what if we were to do like x equals 3? Oh, okay, never mind.
So that would be
That makes sense.
That would be a little bit of a harder descriptor, but I would say that as you approach 3 from the left, the derivative is approaching 0. As you approach 3 from the right, the derivative is also approaching 0. Again, that's just based on a graph, and graphs are going to be notoriously hard to read, right? We could show a graph up there, and you could be totally fooled as to what it is, or you might have it right, depending on how far it's zoomed in or zoomed out. And so I'm going to try to focus on points that have like special stuff going on, like the point of non-differentiability. But you could do the 3. The 3 is pretty reasonable. I think it would be really hard to do the 2.
What do you come up with like the same thing?
What, say again?
Because you'd have like
Because you'd have what?
you'd have like a different slope from both sides on.
And you're still talking about the 3?
Yeah.
Not true. Because as you get closer and closer and closer to 3, from either side, you're going to be approaching a slope of 0. How close could you get to 3? Really close. I mean, seriously, like you might say, I can get really close to 3. How about 3 and a billion zeros and then a 1? That's real close to 3, right? And I could be like, I got you beat. 3 and a trillion zeros and then a 1. And then couldn't you beat me again? We could go back and forth until the day we die, and we still wouldn't be at 3, but we'd be getting closer and closer and closer and closer and closer and closer and closer. And as you do that, you're heading towards a slope of 0 from each side. But if you ever stop and say, okay, if you stop here and stop here, yeah, they'll be different, but as you get closer and closer and closer, you're heading towards a slope of 0. That's a pretty deep question, right? We're talking about like what even is a limit. That's kind of what you're getting at. And the limit, there's no end to the closer and closer and closer idea of a limit. It's a good question. Anybody else? I like the what if stuff. Anything else? Okay, so then the last piece of this question says, then sketch a graph of f prime. And this is what we did before, but this has a special feature to it. So I want to kind of take you through this one. And I hope that you'll see a cool connection between what we just set up there in green and the graph that's about to show up. So here's how we do this. I am going to write my zeros of f prime up there first. So as you look at the graph of f, how many zeros do you see? How many zeros of f prime? Sorry. And where would the 0 for f prime be? When x equals 3. Yeah. So I'm going to come over here and I'm going to graph this. And I'm going to put a 0 for f prime right there at 3. I have to add one little piece into this, though, because we have a new feature on this graph. I'm going to start off by graphing all my zeros of f prime, just like that one right there. But I'm also going to make a mental note about any points of non-differentiability. I'm not going to put those in there yet, but I'm going to make a mental note, and I'm not going to forget. I'm going to be like, all right, there was a point of non-differentiability, and that will show up as kind of a special feature on our f prime graph. But it's going to just naturally show up. You'll see it here in a second. So let's start on the left, as I look at this red highlighted stretch on the graph of f, let's go through it again. I think repetition is good. What could you say about that part of the graph of f? F is linear, and specifically, no, f is not positive because right here, f is negative. Right? So let's go back. So on that stretch, f is increasing or decreasing? F is increasing. Therefore, the slope of f is positive. Therefore, f prime is positive. All right, does that make sense? And not only can we say that on that part of the graph, f prime is positive, we can say specifically that it's, yes, but we can say the slope of f is specifically 2/3. Yeah, we can get really specific on this one. We already figured that number out right there. So now on my graph of f prime, I can come over here and say, all right, well, from -4 getting towards 0, I don't know, this looks like about 2/3 to me. I'm going to stop short of the y-axis because I've got that point of non-differentiability here. I'll skip over the x equals 0, that point of non-differentiability, and let's take a look at this blue stretch right here. Oops. All right, on that stretch, what can we say about f? The graph of f is decreasing. Therefore, the slope of f is negative. Therefore, f prime is negative. All right, so that means our graph of f prime is going to show up below the x-axis. So I don't know where you want to start this, and frankly, I don't really care as long as it starts below the x-axis. How about right there? If you had that, I think that's fine. If you had that, or that, or that, I think all those things would be fine because they start below the x-axis and they head towards our 0. I'll just go with my original. And then on this lovely green part, what could we say about the graph of f? It is increasing, therefore the slope of f is, therefore f prime is positive. So that's going to show up above the x-axis, so how about that? So let's go back to what's going on at x equals 0. What do you guys see? What do you think is going to happen right there? A jump. And a special jump at that. Remember we said earlier that when x equals 0, f prime doesn't exist because f is not differentiable. Right? F prime just simply doesn't exist when x equals 0. So you're right, we will have a jump at x equals 0, but it's a special jump. Can you think you can describe it?
Holy jump.
A very holy jump, yes. Double holy, right? So it's a double open. So it's an open up here and an open down there. So from the left, from the right, f prime doesn't exist. And remember, if you fill in one of those circles, doesn't it mean that whatever it is, it's there? If it's f prime, it's f, whatever it is. If you fill in a circle, that means the value of f or f prime is right there. And f prime simply doesn't exist when x equals 0, so we can't fill in either of those. We leave them both open. So it's double open jump. In fact, I'll go ahead and make a really broad statement that if the graph of f has a point of non-differentiability, like a sharp point specifically, that means that the graph of f prime will always have a double open jump. If f has a sharp point, f prime will have a double open jump at that same spot. Make sense? Can you also see how this stuff in green is nicely illustrated by the graph? So if you look at this that I'm highlighting in blue, do you see that right here? The limit as you approach 0 from the left of the derivative there is equal to 2/3. And then the thing that I'm highlighting in purple, like so, is illustrated right there. And so maybe you can see that double open jump happening based on the values of 2/3 versus negative. Anything? Any questions? You guys seem like you're doing okay? Okay, awesome. So we're going to do one last thing here before we move on to your quizzes, and it is the final example. No, it's not the final one. We'll do the final one tomorrow, but we'll do this next one here, the right here, number 2. Take a minute, read that over real quick. I'll read it out loud. What is the value of k plus c if f of x equals that piecewise and it's supposed to be everywhere differentiable? By the way, this is an old AP question. I think this is your very first old AP test question. We'll do tons of these kinds of things throughout the year. Do you guys, one thing I do want to say, do you guys remember from pre-calc, I think no matter which pre-calc class you had, didn't you guys do a little bit with the power rule? We haven't officially covered that in here, but we'll use that a little bit on this one to kind of get us going with it, just so you guys know. Okay. All right, so what I'm about to write, please don't write. Okay? Unless you want to squeeze it in a corner, it might be worthwhile, but please don't. I'm going to take a lot of space with this. This is not the main thing, but I want to kind of illustrate what we're doing here. If you guys were going to look at this as a piecewise graph, take a look at that top piece, the 2kx squared minus x. On a graph, what would that look like? Yes, it's parabola, absolutely. What about the lower piece? It's a cubic, yeah. So what I'm going to do is I'm going to draw in the cubic here. The cubic is x cubed plus cx. And so that cubic is going to be generally increasing from left to right. So maybe the cubic looks, I don't know, something like that right there. I don't know that that's what it does look like. I'm just throwing out a random cubic. And it would be a filled-in circle right here because it's got the or equal to on it. And then we've got the other piece, which is a quadratic, which would graph as a parabola. And that k is in a pretty strategic spot. Think about all the things that k could affect. For instance, if k was negative, the parabola would open down. If k is positive, open up. If k is a really big number, the parabola would be, say again? Like what if k was like 100? The parabola would be very steep, skinny, something like that. Yeah. What if k was like 1/50th? The parabola would be very fat and wide, right? So k has a lot of power over this parabola. So the parabola could do all kinds of stuff. The parabola could look like this. Well, that graph would be not continuous nor differentiable, would it? The parabola could do this. Same issue, not continuous, not differentiable. The parabola could do this. And that would be continuous, but it looks like it's not differentiable, right? It's got kind of a sharp point going on. So that's not an issue. There is only one arrangement that works here so that this whole graph will be continuous and differentiable everywhere. And maybe it would look something like this. Do you see that? Do you see how it's continuous and differentiable? There's only one way to make that happen. If I'm off by even a little bit, it'll do this. It's not continuous nor differentiable. Or if I'm off by a little bit in a different way, well, then now it's too steep, and it doesn't match up slopes, right? And so what we're going to do is we're going to try to figure out k and c so that this works out to be continuous and differentiable everywhere. And you can do this a number of ways. You could just start guessing and checking, but you will likely die of old age before you figure it out, or die of hunger, perhaps. I don't know. It's going to take a long time just doing guess and check with these, and I don't want you to have any issues like that. So I'm going to show you a better way. Does that make sense in general, what we're trying to do? Okay. So here's how we do this. I've mentioned this already. If you watch the video, you know that differentiability implies what? Continuity, that's right. And so if I'm asked to make something differentiable, they are implying they also want me to make it continuous. And so that's what I'm going to start with. I'm going to just label this. I'm going to say continuity, and I'm going to try to guarantee continuity first. If I'm going to really describe anything about continuity, I have to start off with a pretty standard statement. And what does that always involve? One-sided limits. That's right. So one-sided limits, and the number I care about is 3. So I'm going to write the limit as x approaches 3 from the left. And from the left, would from the left be the cubic or the quadratic? It's the cubic. Yep. So it'd be x cubed plus cx. That's supposed to equal the limit as we approach 3 from the right of the quadratic, which is 2k x squared minus x. And that's supposed to equal f of 3. So that's your standard continuity statement. I'm trying to show you really good notation. I'm not trying to cut any corners here. Hopefully that makes sense. All right, so whenever you have limits like this, what might be a good strategy to use to figure out what the limit is? Just plug it in, see if it works. And if it works, great. And I think it does work. If you do this, you end up with 27 plus 3c equals 18k minus 3 I could repeat myself. F of 3 would be the 27 plus 3c again, but I don't really need to repeat myself, so I won't. We have an issue, though. We haven't made any mistakes, but we have an issue. What's the issue? Yeah, 2 variables, 1 equation. Not so good, right? So we got to come up with a different equation. What is the one piece of this question we haven't even addressed yet?
F of 3.
No, we did, because f of 3 is right here. 8 plus c, k plus c. Well, yeah. We need an equation, and k plus c is not an equation. We haven't addressed one massive concept. I can't understand you when you talk like that. It might just be my ears. The word is up there. Differentiable. We haven't guaranteed anything about differentiability, have we? We have guaranteed continuity by writing our cute little continuity statement. That's great. Done a good job with that. But we haven't guaranteed anything about differentiability, and that's what we need to do. So my next step is to write, is this differentiable? Differentiable. Or differentiability, something like that. Okay, so in order to deal with this, I need to figure out what my derivatives are. And so to do this, this is where that little, the power rule comes into play. And so please forgive me for having you do this before I've officially taught you the power rule, but I'm assuming that maybe you remember it because it's actually really easy, right? If you remember it. So remember that k is a constant, remember that c is a constant. With that in mind, what is the derivative of 2k x squared? 4kx. And then the derivative of minus x would be minus 1. Good. So if you're looking at that and you're thinking, what? Don't worry about it right now. We'll talk about the power rule really soon, I think tomorrow, and you'll see that it's really straightforward. Okay, what about the derivative of x cubed plus cx? Plus just a c. Yep. I'm going to write this for x less than 3, and I am leaving the or equal to off of that because I don't know that this is differentiable yet. So I can't put the or equal to on there because the or equal to implies that we already know that it's differentiable. If you did put the or equal to on there, I'm not going to get really that upset. Okay, so remember that kind of at its core, differentiability is talking about, does the derivative from the left equal the derivative from the right? Sounds like a limit, doesn't it? So I'm going to write the limit as x approaches 3 from the left of f prime has to equal the limit as x approaches 3 from the right of f prime. So when I think about the actual rules for those two pieces, from the left is the parabola, the 3x squared plus c. So that would just be 27 plus c, right? When you directly substitute into that. And the other one would be what? 12k. 12k. Yep. Direct substitution works again. So what's nice about this? I've got an equation in 2 variables. I've got another equation in the exact same 2 variables. So what method could I use? A matrix, sure. I think it would be faster to use substitution or elimination, to be honest. And something to think about is this question, if I remember correctly, was on the no calculator section. So you could still, if you can do an RREF on paper, be my guess, but it'd be faster to do substitution. So anyways, but your idea would work too. All right, so I think substitution would be the better method. Let's take a minute and practice this, just in case you're a little bit rusty. What do you guys think would be the better variable to solve for if we were going to use substitution? C, yeah. So I'll squeeze this in down here at the bottom. C would equal 12k minus 28. And then I could take that 12k minus 28 and substitute it into the other equation for the C value, and then I'm off and rolling. So I'll just work quietly up here and let you guys kind of work on your own as well. Feel free to look up there if you want. I'll try to not make any silly arithmetic errors. I got that. And that. Trying to shake the rust off of the old algebra skills. Hopefully that's not too bad. Like I said, this is an old AP question, so I think they did the K plus C thing just to make it just a singular answer versus, and I think this is an old multiple choice. Be a little bit jumbled if you had all the K's and C's floating around out there. So, you guys have any questions? Go okay? Remember I said something about this in the, we did a question like, do you remember doing something like this earlier with continuity? Remember I said like find B to make this continuous everywhere? This is obviously a little bit of a level up because we're talking about differentiability, not just continuity. Remember I said something along the lines of the odds of you seeing something that on a quiz really, really strong? I would say the same thing about this. I would never, in fact, like I said before, I would never look at any example we do in class and say, yeah, I highly doubt he'll put that on a quiz. Will, have done it. We'll do it again. Whatever. Just be aware. Okay? All right, we will save the next one for next time. I'm going to stop this for now. And I believe